Hello, Dr. and Mrs. Whitehead, and everyone who could be watching. My name is Ishika Jain. I'm part of the Department of Chemistry here at USF. I'm currently a fourth-year undergraduate researcher in the Karney group. We focus largely on physical organic chemistry, and we use computation to explore questions about how and why, reactions work. I'm here to talk about quantum chemistry and organic reactions, specifically how this really crazy phenomenon called quantum tunneling plays a role in cascade reactions and making natural products. So, there are a lot of natural products that include this really specific structure called a bicyclooctadiene, highlighted in red here, or BOD as we like to call it. These natural products are found in a lot of things, such as organisms in the ocean, on Earth, and even in ourselves. So they're very widespread application, right? What's really interesting is that these structures arise from a two-step electrocyclic cascade reaction, from an 8 pi electron to a 6 pi electron electrocyclic reaction. This cascade proceeds non-enzymatically and proceeds thermally, making it viable to explore kinetically by computation. But in order to understand kinetics, we have to consider two possible things. We have to consider the classical mode and the non-classical mode. Depicted here is the 8 pi, 6 pi cascade as it progresses through with varying energy levels and the structures required. In red, we have the classical overbarrier path, and in blue, we have the quantum tunneling path. What tunneling is that it is a quantum mechanical phenomenon that results from a wave model, right? But, quantum mechanics aside, what is it really? Tunneling is the ability to pass through a finite potential energy barrier rather than going over it, provided that this barrier is narrow and not as high, right? You could think of this like a shortcut, essentially. It is a shortcut through a gigantic mountain. And because of that, it affects rate constants, which further affects sort of the speed of these reactions. It's a shortcut, essentially. Experimentally, we see this as anomalous Arrhenius values or activation energy values. We see these as temperature dependence of effective EA, or sort of, reasons why this reaction wants to take the shortcut. And we also see them in kinetic isotope effects, right? But in order to explore tunneling in the 8 pi, 6 pi cascade, we wanted to explore structures that mimic these natural products and sort of the different methyl groups that's on them, right? So first, that means we need to assess what happens to the structure when we add these methyl groups. And two, we need to explore sort of the effects of these methyl groups on carbons that end up joining together when they cyclize both in the 8 pi and 6 pi part, right? And third, we wanted to establish trends and probabilities for tunneling in this cascade. Or, to boil it down, what causes reactions to take this shortcut, right? I've chosen a subset of 5 reactions to focus on. A reference system here with no groups on it, and then a dimethylated, B through D, and then a trimethylated structure in E, right? The reason for this is because, as you recall, many natural products with this motif, such as this immunosuppressant here, have a very specific methylation pattern, sort of in an alternating way, essentially, right? And because of this, this makes this sort of an interest to study in this cascade. But how do we do that? First, we need to find what it looks like in 3D space. We need to find the optimized geometries of the reference system, right? And we found that addition of the methyl groups did not really change the distances too much from the reference system. But what's really interesting is that at really specific points, there are really specific shapes. In the 1A part, there's a helical conformation, and in the midpoint part, the sort of 2A structure, there's a tub conformation. What this means is that these carbons, by design, are much closer together in 3D space than they naturally are, which means that, as a result, sort of the barriers are going to be affected as well. The carbons don't have to move as much, so meaning that, they're more likely to react, essentially. In both electrocyclic reactions, the carbons have to come together to form a bond, move around the same distances, 1.6 angstroms, right? And, distances aside, if you want to look at the energies, we can see that, at 298 Kelvin, the free energies here, adding these methyl groups increases the energy in all forms. However, it drastically increases the energy in the transition state of both, reactions here. This 8 pi part and the 6 pi part here. There's a difference of, 9 or so kcals in the 8 pi part, and a difference of 6 or so kcals in, the 6 pi part. We want to extrapolate. Right here, we see that comparison between a reference system and a dimethylated, system here. There are really big energy differences. But, we know that adding these methyl groups really does change the energy, but more so at the transition state parts, right? We can actually see these when we start plotting out these energies in a, in a curve. Essentially, we start generating a curve, right? So if we generate our intrinsic reaction coordinate here, or what's happening in the reaction for the 8 pi part, we can see that the barriers are really small. The heights are, less than 12 kilocalories per mole. It is highly exothermic, means that it is really downhill energy. Like we think of it as like a roller coaster, it's just like flying by down, right? And then at the very tail end of the reaction, sort of on the right side, the product side, we see that there's a conformational relaxation of the cyclooctatriene, right? Which is really cool because that means that it's setting up this shape for the 6 pi part, right? And we can see in this GIF here how the molecule has to sort of bend itself in a specific way to get to that tub form, right? And if we go towards the 6 pi part, we can see that the barriers are much more taller than the 8 pi part, like 30 or so kcals per mole, like holy hell. But the barrier heights don't really change that drastically with the various methyl substituents. All are so like 30 or so kcals per mole. What's really interesting is that the barrier widths actually increase as we sort of adjust these position of methyl groups, right? But there is not that much conformational relaxation here. And the GIF, you can see that because of that tub form, the carbons that are joining together are much more closer than needed to. And it's sort of bent in a specific way that doesn't really have to adjust that much as it falls down to a transition, or as it falls down to a product side minimum, right? But if we want to look at the rates, we can look at it here. In the top plot is our 8 pi part, and the bottom plot is our 6 pi part. And in this Arrhenius plots here, we're plotting both the over barrier path, our classical model, and our through the barrier path, our quantum model here. In the solid line, we indicate rate constants without tunneling, and in the dotted line, we include rate constants in the actual, and we include tunneling in the rate constants. And remember that tunneling is providing a shortcut. It's providing a need to kind of speed a reaction, not really need to go to the very, very tip top of that mountain, really go towards that transition state energy, which causes these Arrhenius plots to actually deviate from the classical model, right? And in both plots, we can see that there is a slight, contribution of tunneling here, more dramatically in the 6 pi part than the 8 pi part. But if we want to summarize what we see here, we see that there is a small deviation in both plots that indicate a moderate contribution of tunneling, but no actual dominance of tunneling towards the overall rates. And if we want to look at this numerically, we can extrapolate these values and sort of get a ratio of it to actually get the tunneling percentages. In this sort of table here, there's a lot of numbers here, but I've chosen 3 specific biologically relevant temperatures from, 0 Celsius to around 45 Celsius here. And I'm, chosen to compare the reference system to a dimethylated system in the bottom. What we find is that in the 8 pi parts, in the 8 pi electrocyclic reaction, there are lower contributions of tunneling, but there's significantly faster rates because it's so downhill in energy. However, in the 6 pi part, we can see there is, much slower rates, but there is a moderate contribution of tunneling. And the rates at high temperatures are much more probable. Looking at the percentage of tunneling here between 2A and 2C here, around a third to a fifth of the reaction is proceeding, by tunneling. It's proceeding by the shortcut, which is a really good sign here. Interestingly enough, this is actually really good data. There is tunneling. There's not that there's no tunneling. The fact that there is tunneling, even at the 6 pi part, means that 8 pi part is sort of driving this reaction forward. We wanted to make some conclusions here. What can we see, right? We can see that adding the methyl substituents greatly increases the barrier width and height for both electrocyclic reactions, which kind of results in lower contributions of tunneling to the overall rates, but it's still a substantial amount, right? We see there is much faster rates for the 8 pi part because it's so downhill energy, but for the 6 pi part there is sort of decent amount of rates, just a little bit slower. When combined together, this allows for the entire reaction to proceed without enzymatic assistance, or proceed thermally, because it's driven almost essentially by a total difference in energy, like entropically and also enthalpy as well. Tunneling calculations revealed that there is lower tunneling contributions in 8 pi part, but there's moderate amounts of the 6 pi part. If we think of this like a roller coaster here, the downwards momentum, or sort of downwards fall of the 8 pi electrocyclic reaction is driving the electrocyclic reaction of the 6 pi part much further. That's really good. That's really good, right? If we sum it up, what do we find here? We find that these values suggest that tunneling actually does contribute significantly, but does not dominate the thermally allowed 8 pi and 6 pi cascade, right? Future work involves more calculations with natural products containing the BOD moiety, as well as sort of teasing out more sort of reasons why reactions want to take this shortcut rather than go over the barrier, essentially, right? I'd like to thank the Karney Research Group. Over here, we got Dr. Karney. Over on the left, we got Amanda, me, and Ben. They helped me a lot, and their effort is very, very nice. We have Dr. Karney and Dr. Castro. I'd like to thank them for their guidance and support and also work, and to help me both in my research and also the conferences where I have to defend the work I've done, right? In addition, I'd like to also thank Dr. and Mrs. Whitehead and their generous financial support to sort of help me, proceed or take this research to another step, right? And also, I'd like to thank everyone for listening here. Tunneling is a really hard thing to grasp, so I'm really happy that y'all are sticking through here, right? Thank you very much for listening.